This video is going to focus on another simple machine known as the screw. The screw is basically just two components. It's an inclined plane wrapped around a cylinder, and that forms the path and the pitch. To create your own screw, you can just simply take a pencil, cut out a large triangle, and wrap it around. That's what's going to give you a screw. As the screw is used, you can hopefully imagine kind of walking up this inclined plane that just keeps wrapping around and around our cylinder. To actually use the screw, you got to imagine a wheel and axle used to create a rotary motion. Screws can typically do two things. They can change rotary motion into linear motion. This is actually the first purpose of the screw. If you take a look at the picture kind of on the right, that's an example of an apple press. As the little boy walks around in a circle, as he's doing that, this just keeps getting further and further down in that bucket. The more common use that we think of is that it's used as a threaded fastener, so to hold two pieces of wood together, for example. A screw's mechanical advantage depends on how close together the threads of the screw are, and then also how wide the head is where you're turning it. You can get more power by making the threads closer together. So picture the screws on the bottom. This screw has more power than the one above. Okay, there's a lot more threads per inch wrapped around that screw. We can also get more mechanical advantage by having a longer handle to turn the screw with. We never take a screw and just screw it in with our fingers. What we use is a screwdriver or wrench or another tool that's going to give us more mechanical advantage. If we revisit this picture of the boy using the apple press, he could make this job even easier if the handle that he's pulling on was even longer. So it's a trade-off for how far you want to go around, okay, for each turn of the screw, or would you rather have put more effort in to get it to go down farther? Either way, when we talk about mechanical advantage of the screw, you're going to have a really large ideal mechanical advantage, as I'm about to show you. One of the trade-offs, though, is that you get a large amount of friction loss. There's a few important terms that go along with the screw. When we talk about the effort arm distance, we're looking at the distance from basically the center of the screw all the way out to the edge of the screw. If you're using a wrench or a screwdriver, that effort arm distance would be the length of the wrench that you're using. Okay, so it's based on what you're actually using to make that screw go around in a circle. The pitch of the screw is the distance between the threads, and it would translate into the linear distance traveled if the screw went around one time. When we talk about the diameter of the screw, we're not focused on the head of the screw, but rather the base. When you go to buy screws, there's some thread information that they give you. The first number is typically a fraction, and that's giving you the diameter or the base of the screw as seen here. The second number gives you your threads per inch. The third thing gives you a thread description, whether it's coarse or fine. For our purposes, we don't really care about this third number. We're focused more on this middle number, the threads per inch. What the threads per inch tell us is if I do one rotation, what would that linear distance be? So if I had 13 threads per inch, the distance between the threads is 1/13 of an inch. So in one rotation with the screw, we would go only 1/13 of an inch. Knowing these different vocabulary terms associated with screws is going to help us when we do our mechanical advantage calculations. To find the ideal mechanical advantage of a screw, we're still taking the distance of our effort over the distance of our load. Let's use the example of the 1/4 inch screw to the right. It's a 1/4 inch screw. That means the 1/4 inch refers to the diameter of the screw, and the 20 number refers to the amount of threads per inch. When we're defining the distance of the effort, it's one rotation of the effort arm, known as this, and one rotation corresponds to the circumference. The distance of the load is the linear distance traveled during one rotation of the effort arm. That's your pitch. So in other words, as the screw turns around one time, how far down does it go? So remember, the screw takes rotary motion and turns it into linear motion. Putting that into our equation, we're going to take the circumference divided by the pitch. It's still the distance of the effort arm and the distance of the load, but where we take those measurements is what's different about the screw. The circumference can be found by 2 pi r, and then the pitch we're just going to represent with the letter P. So let's take a look at the ideal mechanical advantage of the screw above if the effort is applied by an 8-inch long wrench. My ideal mechanical advantage, again, is the distance of the effort. So that's the circumference that the wrench is going to go around in one complete turn. So I'm going to take 2 times pi times the radius, which is the 8-inch long wrench handle. That's all going to be over the pitch of the screw. The pitch, again, is how far down linearly it would go in one rotation. Using my notation above, that 20 tells me that it's only going to go 1/20th of an inch downwards in one turn of the wrench. When you type this into the calculator, you get a mechanical advantage of 1,005. That seems extremely high, but it's accurate. Remember, screws are going to have really large ideal mechanical advantages. In reality, though, the screw's actual mechanical advantage is going to be significantly lower. Okay, so let's still use the same screw scenario. So we've got an 8-inch long wrench, and let's say it took us 35 pounds of force to make one full rotation. That translated into 1,200 pounds of force downwards. Just like we've done before, we're going to take the force of the load over the force of our effort. 1,200 pounds divided by 35 pounds gives us an actual mechanical advantage of basically a 34-to-1 ratio. That's significantly smaller than our ideal mechanical advantage. So when I find my efficiency, we take our actual mechanical advantage divided by our ideal mechanical advantage, and we get only a 3.4% efficiency rating for the screw. So where did all of that energy go? It takes a lot of energy, and there's a lot of friction when those threads going through the piece of wood or the piece of drywall, whatever we're going through. So that's why our efficiencies are so low for screws, is because we're losing a lot of energy just in actually getting the two pieces joined together. That concludes our mini lesson for the screw. Please come to class with any questions you might have.